In the world of high-stakes technology, we have come to worship complexity. We believe that to build an artificial intelligence capable of writing code or reasoning through physics, we need a machine of unfathomable scale. Trillions of parameters, hundreds of layers deep, a digital architecture so vast that no single human mind can understand it. We look at these models and see a finished monument. But we are wrong. At the core of every modern giant, from GPT-4 to the models in your pocket, is a single, humble function: the rectified linear unit, also known as ReLU. It simply looks at a number. If it's negative, it becomes 0. If it's positive, it stays the same. This ramp is the heartbeat of modern artificial intelligence. But it wasn't born in a Silicon Valley lab. It wasn't the result of a clean, linear path of scientific progress. To understand ReLU, you have to understand the momentum built over the course of a century. We have to see the hubris of the pioneers who thought they had solved the secrets of the mind with brass gears, and the AI winters that froze their dreams for decades. We have to go back to 1940, a time when the foundations of our digital world were being laid in the mud, not as a science, but as a desperate, bloody attempt to predict the future. In 1913, Norbert Wiener arrived at Cambridge University as a prodigy who had already finished his PhD at Harvard. He was 18 and was about to found the field of cybernetics that would later evolve into modern machine learning. He went to study under Bertrand Russell, who had already finished his attempt to reduce all of mathematics to a set of logical axioms in his masterwork, Principia Mathematica. Russell gave the young Wiener a piece of advice that would echo for a century. If you want to understand logic, stop focusing on the symbols. Start understanding their meaning in the physical world. 27 years later, the physical world was on fire. Wiener was now a professor at MIT, and he was a man possessed. He was a pacifist by nature, but he believed that if he could just solve one engineering problem, he could end the war faster. That problem was the anti-aircraft predictor. If you fire a shell at a German bomber, it takes 20 seconds to arrive. In those 20 seconds, the pilot will try to evade. Wiener realized that the pilot, the plane's controls, and the anti-aircraft gun were not separate entities. They were a single, closed-loop system. To hit the plane, the gun had to think like the pilot. It had to use feedback. Wiener spent the year obsessed with building a machine that could model this loop. He called it the predictor. He filled his lab with mechanical integrators, brass gears that could solve calculus in real time. Technically, the predictor was a triumph of logic. But for Wiener, the hardware was a dead end. The massive brass gears were too slow to track the chaos of real-time dogfights. He realized that the true breakthrough wasn't in the metal, but in the math. Wiener no longer cared about the hardware anymore. He had discovered something far more terrifying. If a machine could use feedback to predict a pilot, then the human brain itself was just a biological version of his brass gears. He had the feedback math, but he lacked the logic to describe the neuron. To find that logic, he needed to find one person in America who understood Bertrand Russell better than he ever did. In 1913, while Wiener was teaching at MIT, a 12-year-old boy named Walter Pitts was hiding in a library of Detroit to escape from a gang of bullies. For 3 days, he sat in the stacks, refusing to go home. He didn't read comic books. Instead, he read Bertrand Russell's Principia Mathematica, 2,000 pages of the most dense, impenetrable symbolic logic ever written. However, Walter Pitts didn't just read it. He found mistakes. Walter Pitts sent a series of letters to Bertrand Russell in England. Russell, the man who had taught Norbert Wiener, was so stunned by the boy's corrections that he wrote back immediately, inviting Pitts to Cambridge to become his graduate student. Pitts was 12. He had no money. His father was a boilermaker who wanted him to quit school and get a job. So at the age of 15, Walter Pitts did the only logical thing. He ran away from home, vanishing into the underbelly of Chicago. Pitts spent his days sitting in the back of lecture halls at the University of Chicago, never enrolling, never paying. He was a ghost. But eventually, he was haunted by a man named Warren McCulloch. McCulloch was a neuropsychologist who was obsessed with the soul. He wanted to know how thought could be made of meat. He met Pitts in a park, and within an hour, he realized that this homeless teenager knew more about the logical structure of the brain than any professor in the country. McCulloch took Pitts in. He gave him a room in his house and a seat at his dinner table. And it was there that the two worlds finally collided. McCulloch was the meat, the knowledge of the biological neuron. Pitts was the logic, the inheritance of Bertrand Russell. And when they finally wrote their paper in 1943, they sent it to one man who could turn their theories into a machine, Norbert Wiener. The student of Russell and the pen pal of Russell were about to build the first digital brain, but they were building it on a threshold that was as hard and unforgiving as the war itself. But before this digital brain could rise, the dream of the cybernetic trinity had to die. At the end of the 1940s, a rift opened. Wiener and McCulloch began to fight over the nature of the soul. Wiener saw the brain as a sea of continuous waves and feedback. McCulloch saw it as a sharp digital computer. Caught in the middle was Walter Pitts. In 1942, a personal betrayal, a lie told by Wiener's wife, caused Norbert Wiener to walk away from his friends forever. He never spoke to Pitts again. For Pitts, Wiener was more than a mentor. He was the logic that held his world together. Devastated, Pitts burned his notebooks, including his secret research on 3D neural networks. He spent his final years in a cloud of alcohol, watching as the field he and Wiener built began to fracture. One piece of this fracture, the logic piece, went to MIT with Marvin Minsky. It became AI, clean, symbolic, and coded by hand. But the other piece, the feedback piece, wandered into the hands of a psychologist at Cornell named Frank Rosenblatt. Rosenblatt didn't care about the beauty of logic. He wanted a machine that could feel its way through a problem. And in 1918, he was ready to show the world his monster. In 1948, the New York Times ran a headline that sounds suspiciously familiar to anyone living in the 2020s. It reported that the US Navy had unveiled the embryo of the electronic computer that would soon be able to walk, talk, see, write, and crucially reproduce itself. This was the Mark I Perceptron. Its creator, Frank Rosenblatt, told the press that within a few years, this machine would be able to recognize human faces and translate languages with perfect accuracy. It's a moment of profound, almost painful irony. Rosenblatt was technically right. He just missed the deadline by about 65 years. To understand why Rosenblatt was so confident, you have to understand what he had done to the McCulloch-Pitts switch. McCulloch and Pitts were logicians. They believed that the brain was a machine that solved true-false problems. But Rosenblatt was a psychologist. He believed that the brain was a machine that learned from experience. He took their binary neuron and gave it weights. He connected it to Norbert Wiener's feedback loops, and for the first time, the machine wasn't just following a logical if-then rule. If it made a mistake, a motor would physically turn a knob to adjust the importance of an input. The machine was tuning itself. This was the birth of machine learning, and it was built entirely on a foundation of hubris. While the Navy was cutting checks, the old guard of AI was horrified. To Walter Pitts, the perceptron was a mess. It wasn't logic, it wasn't statistics, it was smearing the beautiful, perfect 1943 binary switch that was the uncertainty of the real world. McCulloch and Pitts believed that if you couldn't prove why a network worked with symbolic logic, it wasn't intelligence. It was just a black box trick. They began to poke holes. They noticed that because the perceptron was a step function, a hard 0 or 1 switch, it was incredibly brittle. In Rosenblatt's world, the machine was either right or wrong. There was no getting warmer, and because there was no slope on the step function, there was no way to use calculus to guide the machine through complex problems. But this house of cards finally collapsed, not because of Pitts, but because of a man named Marvin Minsky. Minsky was a student of the same 1940s logic. In 1969, he and Pempert published Perceptrons. They didn't just disagree with Rosenblatt, they performed a mathematical execution. They proved that a single layer perceptron, the kind the Navy was funding, couldn't solve a simple XOR problem. It couldn't see a pattern if it was folded. They proved that the switch was logically limited. The impact was immediate. The Navy stopped calling, the researchers stopped publishing. This was the first AI winter. From our modern perspective, it's easy to blame Minsky for killing the field. But in a way, he was the level head the field needed. He proved that you couldn't build a digital brain out of shallow switches. To survive, the field would have to go into hiding for 15 years. They would have to abandon the hardware dreams of wires and knobs. They would have to wait for the invention of the microchip, and they would have to find a way to melt the step function into something smooth. They would have to trade the switch for the S-curve. And in doing so, they would accidentally create a new problem that would take another 30 years to solve. But first, the world had to get deep. By the early 1980s, if you told a colleague at a cocktail party that you worked on neural networks, they would have walked away. It was a career killer, a relic of the Rosenblatt era. But Geoffrey Hilton didn't care about cocktail parties. He lived in a world of standing desks and back pain, obsessed with the idea that the old guard was wrong. He didn't want to teach a computer how to see. He wanted to build a machine that could teach itself. This is the birth of what the industry now calls the deep learning mafia. It wasn't founded in a boardroom, it was founded at the Canadian Institute for Advanced Research, because Canada, unlike the US, was willing to fund curiosity-driven research that had no immediate military application. Hinton was the godfather. Benjo was the philosopher. Li Chun was the engineer. Together, they made a pact. They would keep the neural flame alive, while the rest of the world was frozen in the AI winter. In 1986, they finally found their weapon: back propagation. They realized that if they abandoned the hard switch of the 1940s and replaced it with a smooth S-curve, the sigmoid, they could use the magic of calculus to flow the air backward through the network. They could finally train a deep brain. It looked like the winter was over. However, as they attempted to build deeper and deeper, they encountered a mathematical barrier. The sigmoid was too smooth. It was too polite. By the time the air reached the front of the network, it was so small it had essentially disappeared. The deep in deep learning was becoming a ghost. This is where the story gets complicated. As the 90s progressed, the Mafia found themselves isolated. The mainstream AI world had moved on to support vector machines. Mathematically perfect, predictable tools that outperform neural networks in every category. To survive, the Mafia circled the wagons. They reviewed each other's papers, they cited each other almost exclusively, they used their small amount of Canadian funding to create invite-only workshops where no symbolic researchers were allowed. From a modern perspective, this looks like a closed shop. It looks like gatekeeping. If a rival group were to do this today, we might call this academic misconduct. But to Hinton and his disciples, this wasn't about ego. It was about existence. They believed that if they let the statistical or symbolic worlds into their circle, their fragile neural dream would be crushed before it could ever grow. They were holding their breath, waiting for two things the world didn't yet have: massive amounts of data and a special function. But before these could arrive, they had to survive the most brutal academic war in history. The battle against the statistical perfection of the support vector machine. The Mafia was about to be pushed to the brink. In 1990, a man named Vladimir Vapnik arrived at Bell Labs in New Jersey. He was a Soviet defector. But he didn't bring stolen blueprints or microfilm. He brought a suitcase full of some of the most rigorous, uncompromising mathematics the West had ever seen. For 30 years behind the Iron Curtain, Vapnik had been developing a theory of how machines learn. But they didn't care about simulating the brain. To Vapnik, the neural dream of the Mafia was messy, romantic, and worst of all, mathematically unsound. Vapnik's weapon was the support vector machine. And it wasn't a brain, it was a classifier. While Yan Lichen was in the office next door trying to get neural networks to recognize handwritten digits using messy, fuzzy S-curves, Vapnik was drawing lines. Vapnik's logic was simple. If you could separate two groups of data, don't try to think about them. Just find a line that stays as far away from both groups as possible. This is the maximum margin hyperplane. It was clean, it was fast, and it had one property that neural networks lacked. A property that in the 1990s was considered the gold standard of AI: convexity. This is a convex function. It's like a bowl. In mathematics, if a problem is convex, it means that there's only one best answer, the global optimum. It doesn't matter where you start. If you follow the slope, you will find it. It's provable, it is certain. This, on the other hand, is what a neural network looks like to a mathematician. It is non-convex. It's a landscape of thousands of local minima, traps where the learning process can get stuck forever, thinking it has the answer when the real answer is 2 mountains over. Vapnik famously mocked the deep learning mafia. He called their work alchemical voodoo. He pointed out that they couldn't prove their networks would ever find the best answer. They were just fiddling with knobs and hoping for the best. This war came to a head at the MIST database, a collection of 60,000 handwritten digits that was the Olympic Games of AI. For years, Yam Lee Chan's neural networks, the Lee Chan models, were the champions. But then, Vapnik's team showed that with a simple support vector machine, with no brain architecture, no layers, and no biological inspiration at all, the support vector machine matched Lee Chan's performance. It was a humiliation. If a simple mathematical trick could beat a neural network, why bother with them at all? By the late 90s, the support vector machine paradigm had won. The deep learning mafia was no longer just outlaws. They were considered flat earthers of the computer science world. But the mafia had noticed something that Vapnik had missed. As the datasets get larger, support vector machines begin to slow down. The bowl of convexity was becoming a cage. To break out, they would have to lean into the chaos. They would have to stop trying to make their math smooth and perfect like Vapnik's. They would have to return to the 1940s and find the ramp. The war wasn't over, it was just going underground. By 2010, the deep learning mafia was tired of losing. They were tired of being told that their networks were unprovable. Geoffrey Hinton, now a senior fellow at the Canadian Institute for Advanced Research, had begun to push for more aggressive experimentation. But a technical breakthrough would come from a PhD student at Montreal named Xavier Glero. Glero was a young researcher who didn't come from a background of pure statistics. He was fascinated by the biology of the brain. He looked at Sigmoid, the S-curve the field had worshipped since 1986, and realized it wasn't correct. Because the sigmoid levels off at both ends, it saturates. If a neuron gets too strong a signal, its derivative becomes nearly zero. The network stops learning. Glero and Bengal realized that the smoothing that had saved the field from the 1970s was now the very thing holding it back from making deeper networks. In 2011, they both published deep, sparse rectifier networks. It was a moment of technical heresy. They had proposed throwing away the S-curve and replacing it with a ramp, the rectified linear unit, also known as ReLU. To researchers working in support vector machines, this was nonsense. ReLU has a sharp corner at 0. In traditional calculus, a sharp corner is non-differentiable. It's a mathematical undefined zone. But Glero found in practice, this corner doesn't matter. What mattered was the right side of the ramp. Because the ramp never levels off, the signal, the gradient, never vanishes. It stays exactly 1. This allows the signal to travel through dozens of layers without losing any strength. The world changed in October 2012. Using the ReLU ramp and a massive amount of GPU power, the Toronto team entered the ImageNet competition with a model called AlexNet. They didn't just win. They achieved an error rate so low it made every other paradigm obsolete overnight. The war of the paradigms was over. The neural network paradigm hadn't just survived, it had won. History is often told as a series of radical departures, the old world dying to make room for the new. We like to believe that the intelligence humming inside our GPUs today is a brand new species of thought, disconnected from the past. But as we've seen, the architecture of the future is built from the ruins of the 20th century. We're not just using code, we're using the momentum of a century-old struggle. We traveled from the blood-soaked skies of 1940 to the Canadian underground of the 1990s. We watched the cybernetic trinity of Wiener, McCulloch, and Pitts fracture, separating the messy reality of the feedback from the cold, hard certainty of logic. For decades, the field was driven by a recurring human flaw, hubris. Rosenblatt believed his wires would be conscious by the 60s. The symbolic guard believed that logic could solve the soul by the 80s. Each generation thought that they laid the final stone of the foundation, only to watch an AI winter freeze their progress. ReLU wasn't a discovery of a final truth, it was a ramp that allowed us to bypass the mathematical walls that stopped our precursors. It was a simple jagged function that succeeded not because it was smarter, but because it was simpler. It returned us to the 1940s switch, but gave it the power to scale neural networks to deeper than they'd ever gone before. To look at neural networks today is to feel the momentum of these men and women, but it's also to realize that our foundations are still being laid. Unlike physics or chemistry, where the laws are written in stone, the intelligence we've built is still a black box. We have the feedback and we have the logic, but we are still searching for the laws that govern why it works. We are still, in many ways, alchemists. We have found a recipe that creates gold, but we have not yet created a periodic table to explain why it does. The ghost in the machine is actually a legacy. It's a sound of brass gears still turning in the dark, reminding us that we aren't just building a future, we're building upon the past.